Yeah, I'm sharing screen already. Check. Testing my pen. Okay. Yeah. Okay, so good afternoon. Okay, last meeting we discussed the global stiffness matrix. Okay. This time we will try to derive the same matrix differently. Okay. Okay. As you notice, I use our reference Kasimali here. Okay. Okay. So this is our bar again. Okay. Arbitrarily inclined for a certain theta. And take note, we have here the global axis xy. Okay. But if you look closely along the member, locally it has local axis. Yan. So we have y and x. Okay. We have y and x. And so yeah, I'll let you look at the drawing or the figure and zoom in. Okay, zoom in again. Okay, just zoom it. Wait. Okay, so there. So this is our global axis. So I'll just put in G. And then this is the local axis. If you notice, locally you'll be having deformation U1, U2 vertical, U3 on the other ends horizontal, and U4 on the other ends vertical. So arbitrarily you can displace. Remember, for an actually loaded bar, you have 2 degrees of freedom, no, to displacement. So it's either horizontal or vertical. Okay. Now, of course, if you have local displacement, you will be having local member forces. So you have Q1, Q2, the vertical, Q3, the horizontal on the other end, and the vertical on the other end, Q4. Um, we just did the derivation last time, neglecting the vertical displacement. Okay, so don't worry, you will just add another 0, 0 on the local stiffness matrix. No? Okay, and then okay, on the next figure, you will notice that these sets of forces can also be translated, transformed, no? Transformed on a global sets of forces. Yan. For example, your Q1 is here locally, but you can have F1 and F2 parallel to the global axis. Notice F2 is parallel to the y-axis. F1 is parallel to the x-axis, right? Also, F3 here is parallel to the x-axis, global, and F4 parallel to the y-axis, global. Now we wanted to to get the transformation matrix that will uh, relate the local forces Q to the global forces F. Yeah, okay. And by by equilibrium, okay, or by by component, so this is what we got. If you notice F1, force triangle, F1 is here along the X. And if this is theta, so of course this is theta also here. Then find the component of that. You have F1 cosine theta, F1 sine theta. Okay? How about F2? This is F2. This is the triangle, force triangle of F2. So, of course, F2 is parallel to the global y-axis. If this is theta, this is theta here. And find the component of that, F2 sine theta, F2 cosine theta. Okay, agree? Yeah, okay. So I'll just zoom in a bit. So therefore, on the other ends, you can also find the force triangle of F3 and F4 and find the the component of that. Okay. Now let's go beside here. Okay. Then look closely on the equation of Q1. So what is Q1 now in terms of F1 and F2? So remember, this is local forces on the bar, and F1 and F2 is the global forces parallel to the global axis. So is it right? Q1, which is here, is equal to, so we need to find the forces in the force triangle parallel to Q1, right? So F1 cosine theta here, and then F2 sine theta, this one, right? Okay, how about Q2? Q2 is this. So what are the forces parallel to that? Of course, this one, F2 cosine theta and F1 sine theta. So this is F2 cosine theta and F1 sine theta. So you should be consistent with your sign. If you notice, F1 sine theta is going here. So it negates, no? Going downwards. So this should be negative. Okay, while F2 cosine theta is going upward. Yeah? Just to be consistent with this. Okay. Okay. So if you continue that, do the same with the other ends, F3 and F4. Here's my pen. Okay, F3 and F4. So that means you have Q3, Q4, Q1, Q2, Q1. And as we did last time, express that in matrix. So you have Q vector column matrix is equal to cosine theta, sine theta, 0, 0. Let's try to expand this, no? Q1, no? Q1. So Q1 is equal to F1 cosine theta, this one. F2 sine theta, this one. While Q2, F1 sine theta, right? Negative. Then F2 cosine theta, this one. Okay, so consistent, right? So therefore, we can uh, uh, express this equation in compact form as Q equals TF. So everything here is in matrix. Q equals TF. That means to relate the no to convert, no, to convert the global forces, the global force F to local forces, you just need to multiply that with the transformation matrix T. So this is what we call now the transformation matrix. So, okay. So this transforms the global forces to the local forces. Okay. So I want you to appreciate this because this is very consistent with softwares, in STAAD, in ETABS. If you got local forces or local forces in a member in a beam, to get the global forces. So this is how STAAD transformed that. Okay, so that's it. Q equals TF. So that's our formula. If we do backwards, now if we do backwards, if we do it backwards, so say we wanted to relate the Q, the local forces to the global forces, so this is what we will be getting. Sets of equation. F1 equals Q1 cosine theta, and so on and so forth. Okay, so this is global from the local force. Okay, F1, F2, F3, F4. And in matrix form, this is what you get. And if you express that in a compact formula, F equals T transpose Q. That means this matrix now is simply the transpose of this matrix. See? T transpose. So let's do this manually. No? So I'll transpose this first column. T. Okay. Yeah, so right. Cosine negative sine 0, 0. Look at the first column first. First column. Cosine negative sine 0, 0. Cosine negative sine 0, 0. Second column. Sine cosine. Second row. Sine cosine. Third column. Cosine negative sine. Third row. Cosine negative sine. And then fourth column. Sine cosine. Fourth row. Sine cosine. So, right? So, F equals T transpose Q. So, you just simply need to transpose the transformation matrix and you can relate the local forces to the global forces. Okay. So, knowing that, let's proceed. We can now establish that F equals T transpose Q as we get earlier. And, okay. We know, I just didn't showed it earlier. So Q is equal to KU. This is simply what we got last meeting, no? Wherein uh, F equals in McGuire's notation, no? That is KD, I think. So this is simply this Q equals KU. Okay, Q equals KU. We know this already. And we also know that F equals T transpose Q. Okay. Yeah. So substitute the formula of Q. You got F equals T transpose KU, which is simply this. Right? This is your Q. Okay. Okay. So we've already established that now. Okay. Next is also after this. No, once we establish this, we you can relate the local displacement. This is local displacement. Local displacement and U equals TV. There's a formula U equals TV also. So this is the global displacement while this is the local displacement. So as you notice, to relate the global displacement to the local displacement, you will be using the same transformation matrix. Okay, so by the way, what is the global displacement and local displacement? So as I've shown here, this is the local displacement here, the U vector, and the global displacement are this. So consistently with the forces, they are all parallel to the global axis, right? V2 is parallel to the global Y, V1 is parallel to the global X, so on and so forth, okay? V4. And to transform that, so you will be using the same formula or use the same analogy, okay? Okay, so U equals TV. So knowing that, okay, so therefore, we can now use this formula here, substitute TV, right? Therefore, T transpose, and then K, and then substitute TV, right? Okay. Therefore, now, so this is now our current formula. And this 3 here can be converted to the global stiffness matrix. Because remember, the small k this small k here is the local stiffness matrix. Local stiffness matrix. Okay, and then the large K here is the global stiffness matrix. Okay, there. So in short, the global force F is equal to the global stiffness matrix times the global displacement, which is actually this one. Sorry, our formula F equals KD last time is actually global, right? But what we are getting last time no, in our problem is actually global displacement. We're not getting yet the local displacement. No? We're not getting the local displacement yet. So just to be clear, no, global displacement. Everything we get last time in our problem are all global displacement. Remember the problem here, right? We were able to move 2.55 mm, right? This is global. We haven't related this displacement locally to these bars, right? We haven't did that. And it's all global. And also the problem here, wherein we move 5 mm, this is also global displacement. We haven't get the local displacement of each bar, right? So, okay. So what we are doing now is we wanted to show you the relationship between local and global displacement, because that's what the software does, right? Okay, so therefore K, global K, is actually T transpose KT, right? So transpose the transformation matrix multiplied with the local stiffness matrix, and again multiplied to the transformation matrix, you will get the formula for global stiffness matrix. Oops, sorry. Okay, so for those who took up finite element, I wanted to remember what we were doing before last semester. Sorry, last year. Remember our stiffness matrix in terms of integral is B transpose dB. So very familiar. Right? So we are still using uh, the stiffness matrix is very is analogous to this formula. Right? Okay, and it's such that it's in an integral form. Okay. Okay. So since we now establish that, we can now proceed with the problem. Maybe I can just show you the textbook. So if you operate that, so this is one. Excuse me. So this is the transformation matrix, T transpose, and this is our K local. Excuse me. As you see, it's the same, right? You just need to put in zeros to the vertical displacements. It's all zeros, but it's this essentially it's the same local stiffness matrix we got last time, and this is a transformation matrix. So T transpose K T following this, and you will get this. So which is what we derived last time. Okay. Okay, so let's try to check. So this is, what size is this? 4 by 4. This is also 4 by 4. So everything is 4 by 4. No? So square matrix. So therefore, this is also 4 by 4. Okay. And let's read the definition of stiffness matrix. The member global stiffness matrix, this one, The physical interpretation of the member stiffness matrix is similar to that of the member local stiffness matrix, right? So the Kij represents the force at the location in the direction of Fi required along with other end forces to cause a unit value displacement. So that's what we did, right? We we impose a unit displacement on each end and find the force, okay, on both ends. And that's what Kij represents. Remember, uh, where is our derivation last time? Kij, this one. Let's proceed with the local derivation. This one, right? Okay. So we impose U1. So this one here. So this is K11, right? K11. So K11 stands for the force at 1, right? To cause a unit displacement at node 1. So that is positive 1, AE over L. Okay. How about K12? This is K12. So if we interpret that, the force at uh, at 2 to cause that cause a unit displacement at 1. So which is negative 1, negative AE over L, right? Okay. So in simplest form, that's how you interpret the elements of each stiffness matrix. Okay. So you can you can now realize that each specific address, no, in our matrix has a physical meaning. That's the beauty of the stiffness matrix. It's symmetric. That means to be stable, no, to be stable, the structure should have a symmetric matrix. Number two, it should have a determinant. Uh, the stiffness matrix of a structure in matrix form should have determinant, so that it's not singular. No, that's the physical meaning of a stable structure. Okay. Otherwise, it's unstable, no determinant. Okay. Excuse me. What else? And aside from that, of course, if it's a square matrix and symmetric, yeah, it's transposable. Yeah, you can invert the matrix. Mhm. Okay. So since we now derive that, we can now proceed with the problem. So this time, our solution will now be in line with this derivation. So that's what I'm trying to point out. That's why we need to set this, to establish this, to establish this, because our next problem will be in line with this. The solution will be in line with this. Okay. So let's go back to our previous problem. So I'll just rewrite it. But now it's a different approach. Okay. So this is the problem we solved before. Since we wanted to automate this is a prequel for automation. We need to be consistent with numbering the coordinates. Oh, sorry, the joint. No? And also, while being consistent with numbering the joint, you should also be consistent with numbering of degrees of freedom, right? So as you see here, uh, I numbered the joints 1, 2, 3, 4, 5. Okay. So 1, 2, 3, 4, 5. Okay. We also know that each joint has 2 degrees of freedom. It can translate onto displacement. Therefore, for member 1, 2, our numbering will be 1, 2, 3, 4. and it should be consistent with our arrow because I'm moving upward. Okay, so 1, 2, 3, 4. Okay, since this is node 3, this will be 1, 2, 5, 6. Okay, node 4, 1, 2, 7, 8. And then node 5, for member 1 to 5, 1, 2, 9, 10. Okay, I already wrote down the the matrix, imaginary matrix, okay. So member 1 to 2. So therefore the numbering of our matrix will be 1, 2, 3, 4, consistent with this, with the numbering of degrees of freedom. For member 1, 3, 1, 2, 5, 6, right? Consistent. For member 1 to 4, 1, 2, 7, 8. Okay. And for member 1, 5, 1, 2, 9, 10. Okay. Uh, I hope you get it. Okay. Now let's try now. Let's try now. So that is the local stiffness matrix. Okay, we now established the local stiffness matrix. Okay. Now we need to find the structure stiffness matrix. Okay. To get the structure stiffness matrix, of course, you need to know which degrees of freedom the structure will displace. All right. So that's what we intend to get. No? So how does the software knows that? Of course, if you modeled in STAAD supports on these nodes, therefore STAAD will automatically read that there are restraints on 2, 3, 4, 5, right? If there are restraints on 2, 3, 4, 5, therefore the degrees of freedom 3, 4, 5, 6, 7, 8, and 9 and 10 will be restrained, such that the only remaining degrees of freedom will be 1 and 2. Okay? Right? So because you don't have restraint on node 1, right? Joint 1. So therefore, the degrees of freedom that will be displaced is 1 and 2, consistent with our numbering. So therefore, that's 2 to item. Therefore, your expected size of structure stiffness matrix will be 2 by 2. Okay, 2 by 2. That's why I prepared a 2 by 2 uh, square matrix with a labeling of 1, 2. Okay, that's important, no? The numbering 1, 2. Why important? Because as you notice, I will capture all elements having labels 1 and 2, because that's consistent with our structure stiffness matrix, the required S. Okay, because the formula in Casimal is P equals SD. And to get the displacement, D equals S inverse P here. Okay? And if you check the size of the matrix, our P is 2 by 1 and our S is 2 by 2. Okay, so invert a 2 by 2, it's also 2 by 2. Your P is 2 by 1, so they are compatible. So therefore, the resulting matrix is 2 by 1. Okay. So therefore, all the elements here will be added. They will contribute to the structure stiffness matrix. So if I can show an arrow there, here, arrow, they will all contribute to structure stiffness matrix. So in short, you can right away ignore the values here, right? On the remaining values here, for the purpose of solving only the displacement. No, and only for solving the displacement, global displacement. But if I wanted you to obtain the local member forces and local displacement, of course, you will also need those data. Okay, so how do we implement that? Okay, so basically, I also have a snapshot here of sample Excel. Okay, if we zoom in, okay, so I prepared a, so you will be going to I don't know, to create a spreadsheet or any formula. Okay, so input the coordinates, you will get the length, the Pythagorean square root of x squared plus y squared. Get the corresponding theta or angle, and input the area, elasticity as given in the problem, and find AE over L. And of course, this is the formula we obtained, the global K, and then plug in this AE over L, you will get K. And I highlighted this because remember, this is labeled 1, 2, 3, 4. Okay. Okay, so once you establish that all the case, you can now prepare your S, which is 2 by 2. Okay, and this is your P, 2 by 1. Okay, also your P is also correspondent to the to the degrees of freedom. Diba? So you have degrees of freedom 1 and 2, no? And your P is 1,000. So where is it acting? In degrees of freedom 1 or degrees of freedom 2? Our convention, 1 is x, no? And 2 is vertical. So therefore, it's acting on node 1. Sorry, in degrees of freedom 1. So in matrix form, that is 1,000, 0. So that's why our matrix here is this. And then find the inverse of S, and multiplied with P, you will get the D. Okay, to find the inverse, you will use the in Excel meanverse command, meanverse, and to multiply uh, with the other matrix, you will use mmult. So mmult, of course, S inverse and P. So that's basically your command in Excel. Okay, so let's do this. Where's that? Okay, so this is our problem. Okay, so member 1, of course, this is 3, right? Kasi 45 degrees, right? Therefore, your length is 4.24. Just apply the Pythagorean formula. And to get theta, arctangent, right? Arctangent. And you can convert that in degree, 180 over pi. Okay. And then implementation of the global stiffness matrix equation. Okay. And then everything here multiplied to AE over L. So, oops, you have this. Okay. And just copy paste this whole thing. Copy paste that and just change the coordinates of X and Y and input the area 5,000, right? 5,000. This is 3,000, 3,000, 5,000, 3,000, 5,000, and then 3,000. Okay, and then that's it. Member 4, yeah. And I highlighted all the first 2 by 2 which corresponds to 1 and 2. Okay. So for example, I wanted to remember, we need to get all the all the labels 1, 2. Okay. Okay, so I'll prepare 2 by 2. So prepare 2 by 2. Much better if you put in colors na, no? Para yan. So 2 by 2. So equals. So this is this plus this plus this. Okay, plus and then this. Okay, and then enter. So since that is consistent, so I can just copy paste na lang, no? Control C, Control V, Control V, Control V. Okay, so this is our S matrix. So structure stiffness matrix. Therefore, you can now realize that the structure stiffness matrix is the matrix of the structure with all the supports incorporated na. No? Okay, because the S is now dependent on the number of supports, on the location of the supports, right? So therefore, the system, this 4-bar system, can have different different structure stiffness matrix depending on the location of the supports. Okay. Okay. How about P? So I've already shown you that is 1000, 0. Okay. Okay. 1000 and 0. And so D equals S inverse P. So we need to find the inverse of this. Okay. So I'll prepare a 2 by 2 again. The inverse. So this is the trick, no? This is the trick. Highlight this 2 by 2. Okay, and then after highlighting, press equal. Press equal, and then after pressing equal, type in mean verse. Mean verse, and then open parenthesis, then select the S matrix. After selecting the S matrix, close parenthesis, okay, and then press Control Shift Enter. Control Shift Enter. So that is your S inverse. Okay, Control Shift Enter. So once you have the S inverse, multiply with P and prepare a 2 by 1 matrix. So highlight again, equals, this time M mult. M mult, that means matrix multiplication. Open parenthesis, select the S inverse, and then comma, select the P matrix, and then Control Shift Enter again. So see, so we came up with the same answer as with the textbook. Okay, so this is in meters. Turns out this is in meters. 2.55 mm or 0.00255 meters. Okay. So if you remember, no, when we solved this last time, we were told already that the displacement, or we assume that the displacement is only on the horizontal, right? Unlike with our solution right now, we approach it in a general manner. We can say that we can expect, since to be consistent with the procedure, there's no that joint can displace uh, in two ways. No? It's either vertical or horizontal. Okay. So such that we prepared a 2 by 1 displacement matrix. Okay. Unlike previously, the solution we did is We just assume that there's only a horizontal displacement, right? So in order to simplify the solution, here we assume that uh, your structure can also displace vertically and horizontally, which is general in approach. Okay, why? No, what if I change the if I change the force? No, I have a component, 1,000, say 1,000 kilonewton. We call this going to the right, and going upward, I have say 200 kilonewton. What will be my corresponding displacement? If you notice, there's now a vertical displacement, no? Aside from the horizontal displacement. Okay, so very very convenient. So let's try to check the consistency with our problem. Okay, continue. So while waiting for STAAD, no, let's solve another problem. Okay, so I also solved uh, the previous problem also, the next problem. So we only have two members, therefore I only prepared two, call this, two local stiffness matrix, this one. Okay. So briefly to show the numbering, we no no we will displace on vertical, as stated in the problem. So let's try our new approach. Number the degrees of freedom. This is 1, 2. This is 3, 4, right? And this is 5, 6. Therefore, the stiffness matrix here is 1, 2, 3, 4. And for the next bar, that will be 1, 2, 5, 6, right? And since we can only displace on 1, 2, therefore what we need is 1, 2 here. And also 1, 2 here. The four datas here, right? And then, but the problem said, what will be the force P equals SD, no? What will be the force if the displacement is 5 mm? So this is already given. Displacement is already given, no, stated. And after getting S, we just need to simply multiply S to D, S matrix to the D matrix to find the P. It's a different problem, no? It's a different uh, unknown. No? This time the unknown is P, not the displacement. So our approach now is simply to multiply S matrix to the D matrix. Okay. So after establishing this, okay, or establish this and establish S, okay, you simply have to, if you check the formula, I simply added them. Okay. Okay, 2 to 2. Basically, this should be 1, this should be 2, and 5, 6. Okay, so this is the S, and the D matrix is this. No? This is given in the problem, 5 mm. So 0, negative 0.005. And then to get P, I only use M mult. I'll show you. No? Equals M mult, S matrix, select this, comma, and then the D matrix. Close parenthesis, and then Control, Shift, Enter. Okay, So what I get is 180.99 and 355. So very similar to the one we obtained, 180 and 355. Now on our problem, what we got is, what do we have here? 183 and 355. No, we get yeah, 181 and 355%. Okay, so the same, no? 181, 355. 181, 355. And 181, 355. Okay, so the same. Okay, let's try. So this is our problem before in STAAD. Okay, so view, front view. Okay, what do we'll try to change the loading. Okay, so instead of 1,000 only, let's try to add 200 kilonewton upward. Okay, modify, yes, close. So there's a 1,200 upward. And then analyze again. Analysis, run analysis, save.
Sir, naka-mute po yata kayo.
I'm sorry. Yan. So by now, I think you can now appreciate the procedure of STAAD. No? So here, he sets up the load vector, P, okay? And then he processes each element stiffness matrix, which we did, right? K1, K2, K3, K4, before getting the S matrix. So once you get the S matrix, invert that and multiplied with P, you will get D. And after getting D, he calculates down the member forces, and so on and so forth. So later na lang yung member forces. Okay,
Sir, just lang po.
yes, sir.
Parang baka po magkaiba sir yung maging output dyan, sir.
Bakit kaya?
Kasi po sir, yung nakaraan pong discussion, dun po sa x-axis na yung may 30 degrees po, ang ginamit nyo po, 3 over sine 30. Kaya 6 po yung nakalagay na ano dyan. Doon po sa coordinates. Di ba po dapat 5.196, 3 over tangent 30 po.
I don't know. Anyway, so what we got is this is the so this is exciting here, no? So 2.63.995. Take note, we use 205 gigapascal. Ano? This one. 205. I need to change each of them. What else? 200, no? Upward. Okay. Ay, dito pala. Yeah, 200. 205. Okay. Palitan ko na lang to. 0.995, 2.63. Although, There's small discrepancy still, right? As you notice, no, 2.63 mm STAAD gets. We get 2.49 and 0.00 or 0.86. STAAD gets 0.99. Very small discrepancy, right? So let's try to mukhang meron siya dun sa let's use default standard, default material. Properties. Change. Yeah. But still, right now, if you notice the very small discrepancy only, okay? But with the help of like spreadsheet we prepared, it's easily verified that the results are there, almost similar. Maybe it's more on ano na lang to, round of error na lang siguro. Post processing. Yan. So this time 2.56.97. Okay? Yan. So that's basically how software did, no? Yeah. It sets up the element stiffness matrix and yeah, find the corresponding displacement. Okay? What problem do we have? Kasimali has problem here. Let's try. So last problem of the day. Kasi we were able to verify naman yung earlier, the textbook problem here.
Sir, may question lang po.
Yes, sorry. Nasikaso lang.
Okay lang po. Sir,
Alright.
di ba possible in STAAD na
Yeah.
inassign nyo po yung property member specification niya as trust? What if, sir, pag ang ginawa na lang natin is nag-release na lang tayo ng moment para mag-behave siya na parang trust member, para imbis na double bending siya, magsi-single bend na lang. Which is yung i-release mo yung moment at X and yung moment at Y. Possible ba siya, sir?
Well, technically possible. Possible kasi yun nga ang pinapakita ko dito is inassume natin siya as hindi ko siya inassume na trust, di ba? But because take a look dun sa stiffness matrix. Uh, ang the stiffness matrix is only capable to displace laterally and horizontally and vertically. Although in general this is a beam element, what do you call that? This is a beam element which has 6 degrees of freedom. 6 degrees of freedom yan. So ang K nito actually is 12 by 12. Pagdating natin doon sa frame topics. This is actually 12 by 12. Each member here, ang stiffness matrix niyan is 12 by 12. While we are only using 4 by 4. Because because by we simplified the problem by assuming only that the member is only capable to displace vertical and horizontal. Which that means, no, although this is 12, although the STAAD is using 12 by 12 matrix, we still able to came up with the same answer. Why? Because you don't have you don't have other force, what do you call that? Say you don't have Z force. So hindi niya ma-activate yung yung stiffness niya on the Z direction. Ang na-activate lang ng member is the stiffness on the XY direction, which is consistent with what we are doing. Parang ganun. Kaya may discrepancy because in STAAD, it's using a 12 by 12 matrix actually because it's a general beam element. Now, since you only have pin support, and pin support mo na yan is only 3 by 3. This is 3 by 3. So, ni-restrain niya kagad yung yung degrees of freedom mo sa 3 displacement. Okay? So, mas ma-appreciate niyo to pag ang atake ko agad is yung frame element. Pero hindi naman as it turns out, very minimal lang yung difference. It's just that it's okay to assume only a 2D, two-dimensional member. Remember, if you check the the command file, we are analyzing in space. So in space yan, so dapat yung K niyan 12 by 12. Because in general, each beam element has 6 degrees of freedom. The X, Y, Z, tapos may moment ka or rotation in 3 direction also. So 6 degrees of freedom here, 6 degrees of freedom again here. So that makes it 12 by 12. Okay, ganun lang. No? So yung sinasabi mo, well, pwede rin, no? You will come up with the same answer for sure. Because magre-release ka di ba?
Opo.
Yan, magre-release ka. Okay.
Thank you po, sir.
Yes, sir.
Ano po pag sa kunwari yung STAAD na exercise yung ginamit, tapos mag-plane analysis pa. So, okay, possible to...
Sige. So, try natin mag-plane analysis.
Yes, sir.
Okay, utilities, command file, STAAD plane. Save. Wala naman akong Z, no? Analysis. Done. Post-processing. So, almost the same pa rin, right? 2.567.97 pa rin. Diba? So, walang walang masyadong difference. Ano yung gagawin ko? Another problem. Just to of course, in our exam, no, you will not be using STAAD. Sa na yun, no? Para kailangan mabata kayo sa manual muna. Is that here? Example 3.9. No, not that. Yan, this one. Pero isa lang din to eh. Okay, so let's solve that. Yan, okay. Paste that here. Then paste. So let's talk about the degrees of freedom. So this one here, this one here, this one here. Masyadong ulit. So first, decide on the node numbering. So this is node 1, node 2, node 3, node 4. Okay, next. Okay, so therefore, if this is node 1, this will be 1, 2. Degrees of freedom 1, 2. This is node 2, this will be 3, 4. This will be 5, 6. This will be 7, 8. Right. Okay. Then for K1, for K1, so this is member 1. 1, member 2, member 3. Okay. K2, then K3. Okay, then write down the corresponding numbering. 1, 2, 3, 4. 2, 3, 4. 1, 2, 5, 6. 1, 2, 5, 6. And then 1, 2, 7, 8. Yan. And decide on the S. What's our S? So you have restraints here. Therefore, you are free to displace on 2 degrees of freedom here on that So S will be 2 by 2. And what 1, 2. That means everything with 1, 2 should be obtained. 1, 2. Madali lang pala to. So that's what we're getting. 1, 2, 1, 2. And they will all contribute to our S. Okay? Okay, so with that, copy ko muna siya. Okay, and then copy the formula. Control C. Control V. Control V. Control V. Number 2. And number 3. Okay. What's the X of number 1? So this is 1. 3, negative 3, no? This should be negative 3. Y is negative 4. And then 3, negative 4. For member 2, 0, no? 0 ang X. Y is negative 4. Okay. So ano siya? Lagyan ko na lang 0.00001. Nag-error siya. Next is positive 3, negative 4. Positive 3, negative 4. Area. 4,000, 3,000, 4,000. So 4,000. 200 pala, no? 3,000. 4,000. Sige, okay lang. 205. Yung default na lang. STAAD gamitin ko. So that's it. We now know K matrix of each member. Then let's establish S 2 by 2. So equals this plus this plus this. Then copy paste na lang, no? Control C, Control V. Okay, then what's our P? Our P is, of course, 1 and 2. 1, 2, and 600. So 1, 2 is, 600 is 1, negative 1, 2, 4, degrees of freedom 2. So find the S inverse. Okay. Gawin natin kulay. So equals mean verse. This, Control Shift Enter. And then prepare a 2x1 for D. Equals M mod S inverse and P. So shift enter. So that's our displacement. So we will be displacing positive 5 mm, no, to the right, and negative downwards, vertical, which is makes sense because our force is going downward and going to the right. Okay, so let's try to model that. Okay, kasi mali. Trust na lang. Actually, in my ebook, I already have those ano eh. Ito, nasolve ko na pala yan. Yan. So using SMAT. Okay. And also, there's a STAAD file also there. Yan. Yan. So 3463. Okay, 3463. 0, 3, 4, 6, and then 3. Okay, and then front view, add beam. Okay, so you should also realize that what although we don't follow the numbering of degrees of freedom, no, we came up with the same answer. Properties. Okay, 4,000, 3,000. What's the diameter of that? 4,000 times 4 divided by pi. This squared. 0.0 still. 0.00 0.07136. Add. For the 3,000, 0.061804. Maybe yung mga rounding off dyan eh. Diyan siya nagkakaroon ng discrepancy. Okay. So this is 4,000. This is 3,000. Okay. And then supports. Add. Okay, next is loading. Then add. Nodal load. Mga 1,000. Ay, limutan. 1,600. Going down, no? Negative 1, 2. Nodes cursor. And then assign. Okay, analysis. Add. And then run. So we should get 5 and 3. Yan. So, almost the same, no? 5 mm and 3 mm. Okay? To exaggerate the displacement here. So, consistent to the right and going downward. Okay. Okay, what else? So, meron pa ba akong ibang example dito? Wala na. Okay. So, I'll try to open my SMAT file for that. Hanapin ko lang, no? Where is that SMAT? Trust. Is this page 109? Tama. Page 109. Oh. Okay. 3 displacements to. Okay, the same. 4,000, 3,000, 4,000. Where is my coordinates? 5, 4, 5. The same. My P matrix is... Bakit 3 by 3 to? Mhm. 0, 0. 3, 0. 6, 0. S4 should be 2 by 2 only. My P is... It's not, it's different. Hindi ito. Okay, this one. Yan. So in SMAT, this is my code for each stiffness matrix. So I loop from 1 to 3 because we have 3 elements. And column vector for each area. And then length. And the corresponding theta. SMAT default is radian. So I should input by radian. Then, okay, so this is your K1, K2, and then K3. So first, that's why in my ebook, you need to prepare a null matrix first. No? The null matrix is correspondent to the size of your degrees of freedom. No? The unrestrained, not the unrestrained. So since you have 2 unrestrained, so therefore 2 by 2. This one, I'll explain later. No? So yun yung pang-automate ko nung stiffness matrix. So this is my S4, 115, 354. What do we get? Almost the same. May konting discrepancy. 115, 354 sa akin. Next is yan, 600, negative 1, 2. Yan, the same, right? 5.2 mm and 3.3. The same with STAAD, 3.3. Okay. Okay, so let's now discuss the global displacement. So after getting the structure displacement, let's now find the global displacement of each bar, diba? So we have this set up. And as we know, each node shall have a corresponding global displacement for each bar. So we know that this is 1, 2, and our numbering, tama ba? Baliktad yata number ko dito. So this is 1, 2, sorry. This is 3, 4. According to the SMAT, no? This is my numbering because 1, 2 is 0 eh. Okay? Therefore, my 3, 4 degrees of freedom or displacement is D1, D2, which came from our answer. Okay, how about V2? This is member 2. This is member 1. This is member 3. So consistent, right? Because the corresponding labeling here is most likely this is 3, 4. 5, 6. 5, 6, 1 to 5, because this is 1, 2, 3, 4. Therefore, this is 5, 6, 3, 4. Okay, 5, 6, 3, 4, while this is 7, 8, 3, 4. Yeah, okay, para consistent. Okay, so they all came from the answer here. Now, from our discussion, F equals KV, right? We know the global stiffness matrix of each member, and knowing the global displacement of each member here, we can find the global forces using the formula F equals KV as we discussed. So using that, multiplying that, you came up with this. So this is the global forces, global end member forces, no? Member end forces. No? So for F1, you have 40 and 53. So you have negative 40. So that should be here. 40 and 53. Makes sense, right? Because you have a force going to the right. Eh. Therefore, the tendency of this force is tension. No? Kasi papunta siya doon, no? Yung displacement niya. Therefore, it will resist the tension. So, going downward sila. Okay, how about here? 0, 57. So, wala kang, 507 pala. So, this will be 507. Okay, 507. Ito pala to. Upward, 507. 507. 559,746. So, try natin 40, 53. 40, 53. Find the reaction, right? Node 1. So, correct, right? Our global reaction is 40, 53. So, that is negative 40 and negative 53. So, consistent with our SMAT implementation. And for node 3, as you see, 507. 507. 559,746. Yeah. Right? Ay, madilim. Anyway, so yan, 40, 40. 507, 507. 559, 559. 740, 740. Okay? So, that's it. I think you can now verify the forces of STAAD, global. Wala pa pala dito yung Q equals KU. So next time na lang. I'll prepare a video for that. Okay, so question po for actually loaded truss. Yan. Okay, sige. So I'm gonna share po na lang mamaya sa Teams yung ating spreadsheet. Okay. So no more questions. So I guess we can end here. Okay. And I'll just upload na lang another solved problems and explanation for this. At least we were able to explore the application of labeling the degrees of freedom consistent with obtaining the S matrix, okay, and then finding out the global member end forces from the global displacement. Okay. So with that, so we can now end. Okay, so see you next time. Thank you.
Thank you, sir.
Thank you
Thank
po,
you po,
sir.
sir. Goodbye po.